Guys, welcoming you all. Today we are going to see about time dependent perturbation theory, Fermi Golden Rule. Fermi Golden Rule. The transition rate and probability of observing the system in a state gets after applying a perturbation to LKH from the constant first order perturbation doesn't allow for the feedback between quantum states. So it turns out to be most useful in cases where we are interested just just the rate of leaving a state. These questions shows up commonly when we calculate transition probability not to an individual eigenstate but an distribution of eigenstate. Often the set of eigenstates from a continuum of accepting states, for instance vibrational relaxation or ionization. Transfer to a set of continuum states from the basis of describing irreversible relaxation. You can think of the material Hamiltonian for our problem being partitioned into two portions. H is equal to Hs plus Hb. Hs and Hb be the two portions plus Vsb of t, where you are interested in the loss of amplitude in the H states as it leak into Hb. Qualitatively, you expert deterministic oscillatory feedback between discrete quantum states. However, the amplitude of one discrete state coupled to a continuum will decay due to destructive interference between oscillating frequencies for each member of the continuum. So, using same ideas as before, let us calculate transition probability from L gets to a distribution of final states pk bar. Pk is equal to bk whole square. Probability of observing amplitude in discrete eigenstate of H0. Rho ek be the density of states unit in 1 divided by ek. Describe distribution of final states, all eigenstate of H0. If we start in a state LKH, the total transition probability of is sum of probabilities shown below. We are just interested in the rate of leaving LKH and occupying any state KKH for a continuous distribution. Pk equal to integral of dek rho ek pk for a constant perturbation. Pk bar equal to integration of dek rho ek 4 vkl square sin square ek minus el t divided by 2h whole divided by ek minus el whole square. Now let's make two assumptions to evaluate this expression. Rho ek varies slowly with frequency and there is a continuum of final state. Matrix element VLK is invariant across final state. The diagram shows the relation between these two. This assumption allows those variables to be factorized out of integral mentioned below. Here we chosen the limits minus infinity to plus infinity since rho ek is both relative to pk. Using the identity, we find total transition probability which is linearly proportional to time. For realization process, we will be concerned with the transition rate WKL, and finally we get WKL equal to integral of dek rho ek WKL. This expression is known as Fermi Golden Rule. Note the rates are independent of time as well as going forward. The first order perturbation theory expression involving the matrix element squared and the density of state is very common in calculation of chemical rate process. Range of variety. The discrete states we saw the first order expression held for VKL less than equal to H cross omega KL and for times such that Pk never varies from initial values. However, transition probability must also be sharp compared to rho ek, which implies given below. So this expression is useful where del E is greater than of WKL H cross. thanking you.